Swayam Prabha. Digital India. Educated India.
We are going to continue our discussions on kinematics of rotation. In this lecture, I am going to talk about the rotation matrix once again. We will recapitulate what we have discussed. Then I will look at combination of rotations. In the previous lecture, we had looked at single rotations and represented the rotation matrix. Here we are going to look at combination of rotations and look at problems. Just to recapitulate, vectors exist by their own right, but their representations in different frames can be different, and in the figure it shows how representations are defined, how the coefficients in different directions are denoted, and the rotation matrix that takes the representation from frame 1 to the representation of the same vector in frame 0, that is shown. And we had looked at the interpretation of these columns, which is very important to write down the rotation matrix, to populate the elements of the rotation matrix. It is very important to understand the interpretation of the rows and columns. The columns of R1 to 0 are the representations of x1, y1, z1 in x0, y0, z0 as the 3 columns. Therefore, the first column is the representation of x0 in x0 representation of x1 in x0, y0, z0. The second column is the representation of y1 in x0, y0, z0, and the third column is the representation of z1 in x0, y0, z0. And we had discussed how these are to be understood. X1 represented in frame 1 is nothing but 1 0 0. If you multiply this rotation matrix R1 to 0 with 1 0 0, 1 0 0 is nothing but x1 represented in 1. Therefore, if you multiply by 1 0 0, it will only filter out the first column, and that therefore represents x1 in frame 1, takes it to x1 in frame 0, representation of x1 in frame 0. Therefore, the first column represents x1 in frame 0, because the representation of x1 in frame 1 is 1 0 0 unit vector. Similarly, y1 in frame 0 is found by by transforming y1 in frame 1, you transform using R10 to get y1 in frame 0, and y1 in frame 1 is 0 1 0. Therefore, this multiplication on the right hand side actually only filters out the second column, and R from 0 to 1 is nothing but transpose of this matrix, and the columns of this R 0 to 1 is the representation of x0, y0, z0 in x1, y1, z1. Therefore, the first column of R 0 to 1, the first column of R 0 to 1, this one, is x0 represented in frame 1, the second column is y0 represented in frame 1, the third column is z0 represented in frame 1. And the rows therefore represents the transposes of these things, because this is this row, the column here becomes a row here, this column is this row. Therefore, this whole row is nothing but the transpose of this column, and so on, and vice versa. Columns of R 0 to 1 are rows of R 0 to 1 are columns of R 1 to 0. This we have seen, we have looked at orthonormality, the dot product of any two different columns is 0, the dot product of any two different rows is 0, the dot product of a column with itself is 1, the dot product of any row with itself is 1. And there is another thing, the determinant of these matrices will be 1 as per our usage of right handed coordinate system. The cross product of the first and the second columns must give us the third column, cross product of the second and third must give us the first column, and the cross of the third and first must give us the second column. Because all these unit vectors are they satisfy this right handed rule. So, cross of x 1 0, so this cross this must be equal to this. Now, let us look at successive rotations, and these successive rotations are always to be given. We will consider this first case when the successive rotations are given about the new frame. For example, initially the brown frame was coincident with the black frame. I gave the first rotation phi about x 0 or x 1, it is the same thing, and I get the brown frame as I have drawn. Now, let us give a second rotation of theta about y 1 or y 2. Imagine that the purple frame was initially coincident with the brown frame. The purple frame was initially coincident with the brown frame. Now, I gave a rotation to the purple frame and we get x 2 y 2 z 2. Initially, it was x 0 y 0 z 0. I gave the first rotation to go to x 1 y 1 z 1, and the second rotation about, so first rotation was about x, the second rotation was about y 1 or y 2 to get x 2 y 2 z 2 frame. All the angles are shown here. Let us write down these transformations, these fundamental transformations about axis. The first rotation r from 1 to 0 is a rotation about x axis, and we have seen the representation. This is the representation and the angle was phi. The first column is nothing but the representation of x 1 in x 0 y 0 z 0, the second column is the representation of y 1 in x 0 y 0 z 0, the third column is a representation of z 1 in x 0 y 0 z 0. Now, let us talk of r from 2 to 1. How did I get frame 2 to from frame 1? I got it by a rotation about the y axis, both y axis will remain coincident. I gave a rotation of theta about y 1 or y 2 axis, but that index does not make any difference. It is same as giving a rotation about say I took an example of rotation about y 0 axis to come to x 1 y 1 z 1, but here we are giving a rotation about y 1 axis, that does not make any difference. Therefore, the first column of this matrix R from 2 to 1, the first column must be the representation of x 2 in x 1 y 1 z 1. The first column is x 2 unit vector in x 1 y 1 z 1, the second column is y 2 represented in x 1 y 1 z 1, the third column is z 2 cap represented in x 1 y 1 z 1. And you will notice that these are the ones. For example, y 2 in x 1 y 1 z 1, y 2 and y 1 are the same, they are co-oriented, therefore, it must be 1 0 1 0. Z 2 in x 1 y 1 z 1, z 2, this length must be cosine theta and this must be sine theta. X component, x 1 component of z 2 is sine theta, y component is 0 of course, because it is rotation about the y axis, and z component is cosine theta. The net transformation from 2 to 0, that is now of importance, that is what I want to find out. Now, the net transformation from 2 to 0, from frame 2 to frame 0, that means if I had a vector in frame 2 whose representation is in frame 2, say p x 2, p y 2, p z 2, what is its representation in frame 0? That means I want to find out p x 0, p y 0, p z 0, like that. Therefore, I want to find out R, the rotation matrix from frame 2 to frame 0, and that is obtained by taking a product in this order. This is very important. Matrix multiplication is non-commutative. R from 1 to 0 multiplied with R from 2 to 1, that gives us R from 2 to 0. So, that is the net transformation. If you just take a product in this particular order, so that in the when I multiply here a vector in frame 2, first after this multiplication I will get a vector in frame 1, the same vector p vector in frame 1. Further multiplication I will get p in frame 0. So, this is 2 and what I am going to get is p in frame 0. If you multiply these two matrices by the standard procedure of multiplication, you will get this matrix. You can again check what is the determinant. You can check whether they are orthonormal. For example, if I take dot of this with itself, if I take dot of this with itself, I get cos square theta plus sin theta sin phi whole square plus minus sin theta cos phi whole square, and that will turn out to be, here I will get sin square theta, here also I will get sin square theta, and here I will get sin square phi cos square phi, that will be 1. So, this I will get 1. So, dot product of this with itself is 1, dot product of this with itself is definitely 1, again dot product of this with itself is 1, dot product of this with itself is 1, dot product of this with itself is 1. So, all of these are satisfied. Now, dot of this with this becomes 0 plus sin theta sin phi cos phi, this dot plus minus sin theta cos phi sin phi, and what is it, these two are equal and opposite. So, that gives us 0. Therefore, this dot product is 0. Similarly, you can check dot product of any two unlike columns are 0. Same thing goes for the rows, and you can take cross product of the first column and second column, you will get the third column, etc. All those properties I leave it to you to check. Now, we will look at this example of yaw pitch roll, combination of rotation. This is a very useful combination of rotation, and rigid body dynamics, when they are studied, a very common way of representing the orientation of a body, of a rigid body, is to use this yaw pitch roll coordinates. Roll is the rotation about the x axis, as I have shown, and the x axis is directed in the direction of motion. The motion direction is very important. Rotation about the axis in which the motion is taking place is called roll. The motion, rotational motion in the horizontal axis, which is perpendicular, the horizontal axis of course perpendicular to the direction of motion, is called the pitch, and yaw is the rotation about the vertical axis, vertical to the body. Then how do I use this yaw, pitch, roll coordinates to represent rotation, general rotation? In the previous case, you see I have used theta and phi. I can also have another rotation about z, for example. Therefore, I will have rotation about x naught, rotation about y 1 and rotation about z 2. I can keep doing all these things, but roll, pitch, yaw is a very useful way of representing orientation. We start with this x 0, y 0, z 0 coordinate frame. We first give an angle, a rotation angle psi, which is called yaw. It is about that vertical z naught axis. So, z naught and z 1 are of course same. The brown frame was initially coincident with the black frame. Now, because of the yaw rotation, it has changed its orientation. And remember that x is the direction of motion, this is the direction of motion. The next thing I am going to give is pitch, which is a rotation about new y axis, which is y 1, rotation about new y axis. Therefore, y 1 and y 2 are identified, x 2 and z 2 they shift from x 1 and z 1 respectively, and the pitch angle is theta. The third rotation is given about x 2, which is the roll. Finally, I give the roll, and you notice that every time I am giving about the new axis. Why I am doing this? The reason is we have a body fixed frame. We have a body fixed frame, and we have looked at rotational dynamics. Body fixed frame gives us a very simple form of equation of rotational dynamics. Therefore, writing it in body fixed frame is very useful, and the moment of inertia tensor is constant, time independent in a body fixed frame, etc. Therefore, we would like to have this orientation representation of orientation of a body using the yaw, pitch, roll coordinates in the body fixed frame. We have therefore first the yaw, rotation about z naught and z 1 is identified, pitch, which is a rotation about y 1 and y 2 is identified, and roll, which is a rotation about x 2 with x 3 identified. I get finally x 3, y 3, z 3 coordinate system. And to represent the rotation of any vector from x 3, y 3, z 3 to x 0, y 0, z 0 is our target. And what is this rotation? The composite rotation matrix, or the combination of these three fundamental rotations. How do I combine them to find out the rotation matrix from 3 to 0? First, I gave this rotation about z 0 by an angle psi, this was the yaw. Then I gave it about y 1 by an angle theta, then about x 2 by an angle phi. This was in our standard representation, this was 1 to 0, this is 2 to 1, and this will give us 3 to 2, and the product in this sequence will give me r from 3 to 0. Rotation about z naught by an angle psi. Now, I am not going to discuss individually, because we have already looked at representation and you have learned how to write down these matrices. Therefore, I will skip the construction you already understand now. First is a rotation yaw rotation about z naught, second is the pitch rotation about y 1, they remain the same as a rotation about y axis, and the third is the rotation about x axis, which is actually x 2 by an angle phi. These are the three fundamental rotation matrices for yaw, pitch and roll. If I multiply these three matrices, I get a complicated matrix. You can check, if you are interested, that the determinant of this is 1, because the determinant of individual matrices is 1. Therefore, the product determinant must be 1, and the dot product of each column with itself is 1, dot product of each row with itself is 1, and the dot product of one column with another, any one, is 0. Similarly, for the rows, this rotation matrix is represents the orientation of frame 3 in frame 0. Why do I say that it represents, this rotation matrix represents orientation of frame 3 or frame 3 in frame 0? Because the first column of this rotation matrix represents x 3 in x 0 y 0 z 0, x 3 in x 0 y 0 z 0. The second column represents y 3 in x 0 y 0 z 0. The third column represents z 3 in x 0 y 0 z 0. That is why I say that this matrix represents frame 3 in frame 0. And by taking the transpose and looking at the columns or looking at the rows directly, you can find out the representation of x 0 in x 3 y 3 z 3, y 0 in x 3 y 3 z 3, and so this is x 0 in 3, this column, the second column is y 0 in 3, and the third so the first row is x 0 in frame 3, second row is y 0 in frame 3, and the third row is z 0 in frame 3. Right. Now, we look at a second case of combination of rotation. What happens if I give successive rotations about our old frame x 0 y 0 z 0? Let us say the brown frame was initially coincident with the black frame. I gave a first rotation about x 0, which is angle phi. The second rotation I give about y 0. The second rotation I give about y 0. This is also very useful in certain applications. If I have to give rotations about an inertial frame, always about an inertial frame, if I want to do that for some reason. So, successive rotations about old frame. Then what do I do? How do I find out the net rotation matrix from 2 to 0? This is the rotation matrix 1, which gives me from frame 1 to frame 0, which is a rotation about x axis, and you will note now from the structure. This is a rotation about the y axis. This is the rotation matrix 2, but which y axis? The old y axis, and you will notice in this second situation now nothing is oriented y 2 y 1, z 2 z 1, x 2 x 1, nothing is aligned, whereas if I had given about y 1, then y 2 and y 1 would have been aligned, but now because I have given about y 0, the next rotation theta about y 0, therefore, it is a general. Now, this purple frame is a general frame, and these two are the unit rotation matrices. Now, how do I combine to get rotation matrix from 2 to 0? And that is obtained. Now, the order, you should note the order, the second rotation appears first and then the first rotation. The order has completely changed. Now, this means the order of rotation, as you give more and more rotations, you can keep giving more and more rotations. For example, you give a psi rotation about z naught, you will have to keep pre-multiplying. You will have to keep pre-multiplying. Then r 3 to 0 is, this was the rotation about x naught, this is the rotation about y naught, this is the rotation about z naught. That will give me the net rotation matrix from 3 to 0. This gets pre-multiplied, whereas when successive rotations are about the new frame, it always is post multiplied. the new frame rotation gets post multiplied in the same order as you give the rotation, but when you give rotations about the old frame, every time about old frame they get pre multiplied, they keep on getting pre multiplied, the newer rotations will get pre multiplied, or the matrix corresponding to the newer rotations will get pre multiplied. Now, this is a major difference and you have to be careful about this. Which axis are you taking in successive rotations, which axis are you taking for giving the next rotation. And why this happens? Because every time, say if what I will do is, now if I have the representation of some p vector in frame 2, then I, by multiplying this, I will get the representation of the same p vector in frame 0. Therefore, here I have this p 2. Now, what this does is it takes the p 2 in frame 0, and that vector again, because how did I get frame 2? I was rotating about y 0 next time. Therefore, this gives us a matrix a vector in frame 0 because of the first rotation, and finally, when I pre multiply with this matrix, I get the representation in frame 0 every time I am going to frame 0, every step, because I am giving rotations about frame 0. And if you multiply, you will get this matrix. Again, you can check all properties of the rotation matrix, they are all satisfied. Let us look at a problem. In the figure shown, the axis x 1 lies in the x 0 y 0 plane and makes an angle 30 degree with the x 0 axis, it has been shown in the figure, while z 1 makes 75 degree angle with x 0. Determine the rotation matrix R from 1 to 0. Now, we will not try to write down fundamental rotations about each axis and try to find this rotation matrix. We will find this rotation matrix solely using the properties of the rotation matrix. Now, how do we go about solving this problem? Remember, what is the first column of R 1 to 0? It is the representation of the x 1 axis in x 0 y 0 z 0. Now, x 1 axis is, it said in the problem statement that x 1 axis is in the x 0 y 0 plane, x 1 axis is in the x 0 y 0 plane, and it makes an angle of 30 degree with x 0, x 1 makes an angle 30 degree with x 0. Therefore, I can directly write the first column. The first column is nothing but the representation of x 1 in x 0 y 0 z 0. So, I can write that. Second column is the representation of y 1 in x 0 y 0 z 0, and it so happens that I do not know any of these elements. Therefore, I keep them as unknowns, R 1 2, R 2 2, R 1 2, 2 2 and 2 3. And this should have been 3 2, this should have been 3 2. It should never be considered that this is a symmetric matrix, these two elements will be same, never. I mean, in general they cannot be in general. Okay. I do not know the second column. Third column, it said that Z1 is what is third column? Third column in this transformation matrix from 1 to 0, it is the representation of Z1 in x 0 y 0 z 0. And what is the meaning of representation of Z1 in x 0 y 0 z 0? It is the angles between Z1 and x 0, cosine of the angle Z1 and y0 and z1 and z0, they are the direction cosines. Now, between z1 and x0 I know the angle, it is specified in the problem, therefore, cos 75, that is the angle, because it was a dot product, remember it was a dot product of the unit vector z1 and unit vector x naught. So, this is cos 75, other two entries I do not know. I do not know the angle that z1 makes with y0 or z1 makes with z0, because z1 is not guaranteed to be on the x0 z0 plane. Now, these are the columns of course. But what I definitely know, this is the property of rotation matrix, that the first column and the third column dot product must be 0. We have been discussing this property. In other words, take the dot product, this is what you will get. From here you can solve for R23. Note this correction, this is 32. You can solve this, this is now known. Next, magnitude of z1 cap, the last column of this matrix, must be 1. Magnitude 1 means its dot product with itself is 1, that is why its magnitude is 1. So, magnitude square is also 1. If that be so, then cos 75 square plus r 23 square plus r 33 square must be equal to 1, and from there I get a condition on r 33 square. R 23 is already solved, this is known. Therefore, I can find out r 33 square, but there will be two signs, because when I take under root I will have plus minus. Now, how do I choose that plus minus? I will choose it from this figure. What is r 33? R 33 is the projection of, or the cosine of the angle between z1 and z0, is the cosine of the angle between z1 and z0, and as per this figure it is an acute angle, therefore, I will take the positive sign. If I take the negative sign, it would be the other axis this way, which is not the one we want. Therefore, we can now solve R 23 R 33. We can solve R 33, this is 33. We will take the positive root. Finally, how do I calculate the middle column? So, the first column and third column now are completely defined. How do I calculate the middle column? I know that this matrix is a right handed, represents a right handed coordinate system transformation. Therefore, the middle column must be a cross product of the third column and the first column, and then I complete the rotation matrix. So, this is a straightforward calculation and I will leave it to you. Second problem, given a 3 cross 3 rotation matrix R, determine the yaw pitch roll angles required to achieve the orientation. We are given 3 cross 3 matrix, suppose we are given a 3 cross 3 matrix and it has been generated out of a roll pitch yaw matrix that we have derived. What will be the yaw pitch roll angles that will produce that matrix? Recall that we had these fundamental rotations about the individual axis for the yaw pitch roll formulation. This was the final matrix. Now, this matrix is now given in numerical terms. Suppose you are given numerical values of each element of this matrix. How do I solve for psi, theta and phi? Let us call that given numerical values in this form R11, R12, R13, R21, R22, etc. The numerical values are known. We have to find out psi, theta, phi that will result in this matrix. Note, from the general matrix, this one, that R 32 by R 33, R 32 is this and R 33 is this, the ratio of these two is tan phi. Therefore, these numerical values, when I take the ratio, that should be tan phi. And if R 32 is not equal to 0, this is not equal to 0, R 33 is not equal to 0. So, for example, if this is equal to 0, then we immediately know what is the value of phi. R 33 is not equal to 0, because if R 33 equal to 0, once again then we that would imply that theta. So, if these are not equal to 0, then theta cannot be pi by 2 or 3 pi by 2, that we definitely know. Rest so if they are both non-zero, I can easily solve. If they are any one of them 0, I can choose, I will know the value of theta, either pi by 2 or 3 pi by 2. Phi therefore can be solved as tan inverse of this, and in most programming languages and in most softwares you have this function called A tan 2, which you should always use to get the correct quadrant. You have to give A tan 2 numerator comma the denominator. In some implementations it is the denominator comma the numerator, that you have to check out, but in a large number of these programming languages it is the numerator comma the denominator, and A tan 2 is a standard function which gives you the correct quadrant as well. Actually it can handle even zeros. Then psi, how do I find out psi? You will note that R 21 by R 11, R 21 is this element and R 11 is this element, and the ratio of this is tan psi. And once again, if theta is not equal to pi by 2 or 3 pi by 2, then you will take A tan 2 or tan inverse and you can find out. And similarly, you can find out theta by taking this ratio. Every time I am converting, I am trying to find out tangent of a particular angle which I want to solve. This is to be able to use the computer in an automatic fashion to get the correct quadrant, and theta is equals to tan inverse of minus R 31. R 31 is this element minus R 31 divided by R 32 by sin phi. Now, sin phi has already been determined in the first step, therefore, I can find out theta. So, to summarize, we have looked at the rotation matrix and their combinations, two types of combinations: rotation about the new frames every step, then it is post multiplied, all the individual rotation matrices are post multiplied to find out the combination or the compound rotation matrix. If it is rotation always about the old axis, then it is pre multiplied, and we have looked at some problems. With that, I will close this lecture.